All right, this is live session 4 for the NPTEL course Introduction to Wireless and Cellular Communications. I'm your tutorial instructor Sachin from the EC department of the Indian Institute of Science. Question 1. Consider the following figure. Hello. Oh, let me check. Okay. The figure is received power on the y-axis and distance from the transmitter on the x-axis. And the question is, which of the above curves approximation shows a curve that considers only path loss? Answer for this you can refer to lecture 15 notes. Um, Here you can see the path loss is just a straight line, and the pink color line shows the effect of large scale fading, large scale effects, and the blue color line, which varies very fast, is the s- small scale effects. So the path loss is just a function of distance, and uh, it doesn't vary. There's only It's only a general trend. So as the distance increases, the path loss also increases. Then the large scale effects can cause changes over a longer period of time, but if you look at 2 points, not time, this is in distance. Uh, but if you look at 2 points which are close to each other, then the large scale effects don't affect them too much. The blue curve, which is the small scale effect, with may change drastically with just the small change in distance. That's where the name comes from also. Large scale effects only vary over large distances. Small scale effects are only show up will show up when the change in distance is small. Then the second question also uses the same figure for the figure in question 1. I'll just copy the same thing. Which of the above curves? Okay, that's a small mistake in my explanation. So when I said the curve B is large scale effect and curve C is small scale effects, you have to remember that the path loss is also present. So it's not just small scale and large scale effects. These curves show the path loss plus the small scale and large scale effects. That's why both the pink and light blue curves are also going down as distance increases. And on top of that, we have layered the large scale and small scale effects. So in question 2, they ask which of the curves contains only path loss and shadowing, which is the large scale effect, but not small scale fading. And you can see small scale fading would mean that when the distance changes by a small amount, there should be large changes in the received power. And you can see that happens only in the blue curve. And that, uh, again, it's from lecture 15 notes. You can refer to that. Of course, even in the notes, the explanation is about the same. There's This is just a general trend. It's not a specific problem, so it's just a brief part of lecture 15. Now we'll look at some numerical problems. So for Q3 and Q4, you have to find the Q value, which you can do using the calculator given in the The calculator, online calculator link should be given in your assignment itself. If the log normal shadowing has a Gaussian distribution with variance sigma is 3 dB, what should be the margin at the cell edge in order to ensure only 2% of outage probability. So we have seen in class that the probability of outage is equal to the probability that the shadowing is greater than your margin, and the margin is the average uh, power received minus the minimum power you need. This is beta. And this is given by, since x sigma is the shadowing which is log normal, this probability is equal to q of beta or sigma. That would mean that beta or sigma is q inverse of p outage, which would mean that the margin is sigma times q inverse of p outage. Sigma is 3 dB, p outage is 2%, which is 0.02. So go and find the value of q inverse of 0.02, put it into the formula, you will get the margin in dB because sigma is in dB. Next, consider a cellular system designed with omnidirectional antennas, omnidirectional cells, but it's actually antennas, and with the farthest point of the cell at a distance capital R and average signal power received at the cell edge PR of D is 1.091 times the minimum power that you need is also called the receiver sensitivity. If you go below receiver sensitivity, your receiver cannot give you any guarantees on the error rate. If you are above receiver sensitivity, then the receiver can guarantee certain bit error rate. If the log normal shadowing has a Gaussian distribution, with sigma is equal to 3 dB, then what is the outage probability? Now we will use the same formula that we used in question 3 for finding P outage. We need the margin and sigma. The margin is depends on the average power and the minimum power. So the average received power is 1.01091 times the receiver sensitivity. And that means beta is the margin, which is the average received power minus Pmin. This is in watts. Since we want the quantity to be in dB, sorry, it's in dB itself. Beta is um, PR in dB minus Pmin in dB. So it's 10 log PR of D minus 10 log Pmin. So beta is in dB, that's why you have to take the received power and Pmin in dB. But this is nothing but 10 log PR by Pmin, which is 1.01091. Because PR is 1.091 times Pmin. And you find out beta, you take the log and calculate the value, then you will get P outage, which is probability that X sigma your shadowing is greater than beta will be equal to Q of beta divided by sigma. So beta is 10 log 1.091, sigma is 3 in this question. Put those values in a Q function calculator and you will get your P outage. Fifth question. A user is traveling in a car that is moving towards the base station to which he is connected at a constant velocity. So this is a conceptual question. I've given values for V, but I won't write it down because it's not necessary. Some positive constant velocity V. At some point in time, the user is nearest to the base station, and moments later he crosses the base station and starts moving away from his base. What happens to the magnitude of the Doppler shift during this time? So we have a base station here, then we have a user is moving with some velocity v, is communicating with the base station. Let's say the angle that his direction of propagation makes, that his direction of his movement makes with the direction of propagation of the radio waves is beta. He moves towards the base station, and at some point he is right below the base station, in which case he is moving horizontally and the base station is radiating perpendicular to the direction of its motion. So beta is a right angle, and then he moves away. At this point, direction of motion is horizontal, and the direction of the wave propagation is this. So beta. So now we have to see what happens to the magnitude of Doppler. Since it's only magnitude, uh, the Doppler shift is v cos beta over lambda, v cos beta into fc over c. We have no control over the carrier frequency. We assume he is communicating with the same carrier frequency, and he is moving at a constant speed. So the only thing that's changing when he moves away, when he moves towards the base station and then away from the base station, is the angle at which uh, angle his move, the direction of his motion makes with the direction of the radio is. So when he's right below the base station, he's making a 90-degree angle. And when he is approaching the base station, he is making some angle beta, this one, which is more than 90 degrees, but less than 180. So in the limit, let's say, he is infinitely far away from the base station, he would be making an angle of pi. That is, his direction of motion would be exactly opposite to the direction of the radio waves. Then once he crosses the base station and moves away, the angle he is making is less than 90 degrees, and the further he moves away, the lesser the angle becomes. And in the limit that he is infinitely far away, the angle that he makes with the base station is zero. So you could say beta goes from pi to pi over 2 to 0. Uh, you look at cos beta is 0 at pi over 2, it's minus 1 at pi and 1 at 0. So initially it's let's look at magnitude of cos beta since we are concerned only with the magnitude of the Doppler shift. So cos pi is minus 1, magnitude is 1. Then when he is directly perpendicular to the base station, the magnitude becomes 0 and then again it becomes 1. So, and okay, from this you can see that when he is moving towards the base station, the Doppler is constantly decreasing, and then when he moves away from the base station, it again starts increasing back to 1. That's mostly just a physics problem. Okay, the next question is consider a user uh, consider a user traveling on a circular road at some speed v miles per hour and let the base station serving the user be approximately at the center of the circular road. The user experiences, there are options: positive Doppler shift. Second option is negative Doppler shift. C is sign of the Doppler shift depends on whether the user is traveling clockwise or anti-clockwise and no Doppler shift. Ah, yes, there won't be any Doppler shift. You can look at the previous question and see that when the user is directly below the base station, he is making an angle of 90 degrees with the, I mean, when I say that, I mean the direction of motion is 90 degrees to the direction of radiation. In that situation, we saw that the Doppler shift was V cos 90 degrees divided by lambda, and cos 90 is 0. So there was no Doppler shift. Same kind of thing happens when he is moving in a along a circle. So when an object is moving along a circle, its direction of motion is tangential to the circle itself. And we know that tangent to a circle is always perpendicular to the radius of a circle, radius of the circle from the center to the tangent point. That is, this is always 90 degrees. So even though he is, regardless of what speed he is moving in, he is always moving perpendicular to the radius. Now, since the base station is at the center, the direction of the radio waves will be along the radius. So he sees no Doppler shift. If you can't remember the formula, then still okay. I can give you just a layman's explanation of what is happening. So, uh, suppose there's a base station and the user is here. The base station is emitting radiation this way. So, at time t is equal to 0, it emits some radiation. Now, if it was stationary, at some point of time t is equal to t1, there would be some component of the radiation that would hit the user. But since the user is moving within the time t1, he would have moved to some other point that is closer to the base station. So what he sees is a radiation which was released much earlier. So in some sense, of course, this is not physically correct, but you can think of the user pushing the radio waves back to the base station, or some kind of compression is happening. So you can think that the radio wave that is released is being kind of compressed and both are moving closer to each other. When the user is moving away from the base station, then the radio waves that are released take longer to reach him. So you can think of this as a kind of stretching that is happening because he is moving away from him. Think of this as this radio waves as a rubber band maybe or a spring. So when he is moving towards the base station, the spring is getting kind of compressed. And you know that if the cosine wave varies very fast, then the frequency is very high. So the frequency increases, the apparent frequency increases when the user is moving towards the base station. And when he is moving away, it's like a stretched spring. So the variation is slow, so the apparent frequency is decreasing. You are seeing a smaller frequency when he's moving away. And when he's not moving away or from the base station, then there's no stretching or compression in the radio waves. So as long as he's moving perpendicular to the base station, there's no change in frequency. So that is a very layman's way of explaining Doppler, but I'm not a physicist, so this works for me. Okay, so if he's moving in a circular path, he sees no Doppler when the base station is at the center. Question 7 is a theoretical question, so I won't answer that. This is just an answer from memory. You can see lecture notes for the 15th lecture. Question 8. Consider a system whose input output relations are given below. Which of them represents a time variant system? Time variant, time varying, same thing. Okay, that's also linear, a linear time variant system. So you have to be careful. They are not asking for a linear time invariant system, they are asking for a linear time variant system. Okay, the options are y of t is x squared of t, y of t is integral of x of tau d tau from minus infinity to t. See, y of t is sinc t times x of t. D is y of t is log of x of t minus 5 to the base 10. Now, suppose the input x1 of t results in the output y1 of t, and the input x2 of t gives you the output y2 of t. Then for a linear system, any linear combination of the inputs, and by linear combination means we scale each of our inputs by some constant. Here I'll take the constants of A and B and then add the two. Then the output should be the same linear combination of the individual outputs. So that is a linear system. Now suppose x of t gives you the output y of t for a time invariant system. If you delay the input by some amount, x of t minus t0, then the output is should be y of t minus t0. What this means is if you do some experiment today and you get some output, and suppose you perform the same experiment tomorrow, you should get the same output. That is, or if you perform the experiment a few hours later, you shouldn't get a different output. You should get the output which is same, but it's delayed by the same amount of time as your input. That's a time invariant system. If a system is not time invariant, we say it is time varying or time variant. This is from your linear signals and systems course. So I won't go into too much detail about that. So here I'll just make a table that says whether the system is linear and if it's time variant. So the first system y of t is equal to x squared of t is it's a squarer, so it's not linear. It's time invariant. So it's actually not time variant. The second system y of t integral of minus infinity to t x of tau d tau. Again, this system is linear, but it's also time invariant. It's not time variant. The final system y of t is log of x of t minus 5. Since you're taking log of the signal, if you add two signals and you add two signals and give that as the input, then we'll get log of the sum of those signals. So if your input is x1 plus x2, your output is log of x1 plus x2, which is not equal to log x1 plus log x2. So the system is not linear. It's actually time invariant, so it's not time variant also. Finally, y of t is sinc t times x of t. This one I'll work it out. So if you give x1 of t, you will get sinc t times x1 of t. If you give x2 of t, you'll get sinc t times x2 of t. We'll call that y1 of t and y2 of t. If your input is ax1 of t plus bx2 of t, then you will get as your output sinc t times ax1 of t plus bx2 of t. But you can also distribute this and write a times sinc t x1 of t plus b times sinc t x2 of t, which is equal to a y1 of t plus b y2 of t. So it is a linear system. Now if you give x of t, the output is sinc t times x of t. Let's call it y of t. If you give the input x of t minus t0, let's do it in two steps. Let's say x dash of t is x of t minus t0. Then x dash of t will give you the output sinc t times x dash of t. But x dash of t is x of t minus t0. So you'll get sinc t times x of t minus t0. But what is y of t minus t0? Y of t minus t0 is sinc t minus t0 times x of t minus t0. Let's call the previous output y dash of t, and you can see that y of t minus t0 is not equal to y dash of t. So it is time varying. So the third system is linear and time variant. Now for questions 9 to 14, we'll use the same data. So in one of the lectures, we saw how to find the distribution of v is equal to square root of x square plus y square, where x and y were independent and identically distributed Gaussian random variables with zero mean and variance sigma square. So we had x and y are independent and identically distributed Gaussian random variables with zero mean and variance sigma square. Question 9 says find the joint PDF of x and y. So since we are dealing with two Gaussian random variables with zero mean, the density of each of them is fx of x. Density of x is 1 over square root 2 pi 1 over square root of 2 pi sigma square e power minus x square over 2 sigma square. Mean is 0. Similarly, fy of y is 1 over square root of 2 pi sigma square e power minus y square over 2 sigma square. Now, since x and y are independent, the joint distribution fxy of x comma y is simply the product of the marginal distributions fx of x times fy of y. We know fx of x and fy of y, just multiply those two and match it with the correct option. Then question 10 asks, define w equals x squared plus y squared, phi equals arctan of y over x. Express x and y in terms of w and phi. And we know that phi is arctan of y over x. So tan phi is y over x, y is x tan phi. But we know that w is x squared plus y squared. Y squared is x squared tan squared phi. Which is x squared into 1 plus tan squared phi. So x is square root of w divided by square root of 1 plus tan squared phi. Now the rest of the part I'll leave it to you. Use trig identities to simplify. So you can use a trigonometric identity to write 1 plus tan square phi in terms of sine or cos. Then you'll get x is square root of w times sine or cos phi. Now once you get that, you can put it back in w is equal to x square plus y square. Y square is w minus x square, which is w minus w over 1 plus tan square phi. Again simplify and write the answer in terms of, so this is y square, you'll have to take the square root after simplification. Now you see that there is a square root of w, so all that's left is to find out whether x is square root of w sine phi or cos phi, and whether y is square root of w sine phi or cos phi. That part I'll leave it to you. Question 11. We wish to obtain the joint PDF of w and phi from the joint PDF of x and y using the transformation of random variables The Jacobian matrix involved in the process is given by. So to transform from xy Cartesian coordinates to polar coordinates, if w phi of w comma phi is the determinant of j times fxy of w comma phi, we know that, where this j is the Jacobian matrix which is asked this question, and that is a matrix of partial derivatives. Dx by dw, these are partial derivatives. So we have found x and y as x is square root of w times sine or cos phi. Whichever one you get, you have to simplify, and y is also something of the same form. I'll just do one example. If a is w cos phi, then dA by dw is, you treat, when you are taking partial derivatives with respect to w, you treat the other variable phi as a constant. So cos phi is a constant. D by dw, the derivative of w cos phi with respect to w, considering cos phi as a constant, is just cos phi. And dA by d phi, when you are taking the partial derivative with respect to phi, you assume w is a constant. So this becomes w into d by d phi of cos phi, which is minus w sin phi. So that's just an example. Here you have to do the same thing with x and y, and you have to note that in this question, unlike the problem in done in class, you have square root of w. So derivative of square root of w is 1 over 2 square root of w. So the Jacobian matrix will be different from the matrix that was there in class. Question 12. Using the above results, the joint PDF of W and phi is given by, and there are a bunch of options. We already know if W phi is determinant of J times fxy of, so you have to write fxy in terms of W and phi. So we found J in question 11, and we found fxy of xy in question 9. So what I mean by fxy or w comma phi is, say fxy of xy was some constant k times e power some other constant c into x square plus y square. Then fxy of w comma phi would be k times, uh, already we they said that w is the random variable x square plus y square. So you just have to replace x square plus y square by w. The constants k and c you have to find by solving question 9 and question 11. Then question 13, from the actually, if you have some other function, say maybe you have something else, g of the form g of y by x, or some function g, then this would be k e power c w tan phi, g of tan phi, because phi was arctan of y over x. So in this case, you will find that g is just the identity function. That is, y by x term doesn't appear in your distribution. There's only k e power w, k e power cw for some constant k and c. So that actually makes calculation of the marginal distributions easier, since you don't have terms in involving phi. So now from the joint distribution, what is the PDF of W? So let's say fxy of, it's actually f if w phi of w comma phi is some a times e power b w. Let's say there's also a function of phi here. Then the PDF of w is the integral. Phi can vary from 0 to 2 pi. Phi is the angle. These are in polar coordinates. So w is the radial distance and phi is the angle. So phi can vary from 0 to 2 pi. A e power bw g of phi d phi. In our problem, g of phi is 1. So fw of w is integral 0 to 2 pi ae per bw d phi. So ae per bw has nothing to do with uh, the angle phi, so we can take it out of the integral. We'll be left with integral 0 to 2 pi of 1 d phi. I'm sure you can do that. Integral of a constant. So here a and b are all numbers you get by solving the previous questions. Finally, the PDF of phi is, so you have fw comma phi of w comma phi. Let's say it was of this form. Then question number 13, option A and D. Yeah? So W is in R plus. R plus means only positive real numbers. Option D says W is in R. That means W can be a positive or negative real number. So in option A, this function fw of W will be of this form. It should be 0 for negative numbers. Option D is something like this. This is just some random curve I'm drawing. I'm not saying that the distribution is this form, but what I'm saying is option A says W has to be only positive values, but option D says it can be positive or negative values. You can see W is x square plus y square. You only think whether x square plus y square can be positive or negative. Okay, in question, once you have the joint distribution in terms of W and phi, you have to, if you want the marginal distribution, then you just have to integrate over all values of W. I'll write here domain of W. So now you see, you need to know whether W is from minus infinity to infinity or it's only from 0 to infinity. Because depending on that, you'll get different answers. So here in this integral, I'll just write domain of W. If I write it down, you'll know the answer. Then you integrate. So since you're integrating over W, it has nothing to do with phi, so you can, and it has nothing to do with the constant A, so you can just write it as A g of phi integral e power bw dw. And you obviously know how to integrate e power something. Okay, once you integrate that, you'll get your answer, and you can choose the right option. So this is the mathematical way of doing it, but you have to, of course, if you don't know what W phi x and y are, this is all you can do. But we know that we are trying to model the gain of the uh, time varying channel. This is trying to model the distribution of the gain considering all the multipaths, right? So if you saw in the lecture, we assumed that the angle of arrival was uniform. What does that mean? In probability, uniform probability means in discrete probability, if there are n different possible values, then uniform probability means each of the outcomes has probability 1 over n. Here, in continuous, since it's a continuous random variable, it won't be 1 over n because it's not countable, but it will be 1 over, it's still uniform. So phi can vary from 0 to 2 pi, and it's a uniform distribution. So if you know probability, you will know directly what the distribution of phi should be for a uniform distribution. Of course, if you don't know that it's a uniform distribution, then you'll have to do all the mathematics. Okay, then we'll only solve 15 to 18 and 19 to 22. They're just theoretical questions. So you can watch the lecture videos, and in some or the other lecture video, the answer will be given. So as long as you watch the lecture videos, you should be able to answer 19 to 22 yourself. So that means I'll do 15 to 18, and for 15 to 18, we have the same problem set up. There's a reflecting wall, and that's the ground or the plane which is horizontal to the reflecting wall, and that's the plane in which you have your transmitter and your receiver. The receiver is moving with constant velocity v meter per second. The distance between the transmitter and receiver is r0, and distance between the transmitter and the reflecting wall is d. So this data will be used for the next 4 questions. Now, question 15 asks you to write down the equation of the received signal. And so the received signal will have two components. One component is the direct radiation from the transmitter to receiver. Another component is the radiation which is transmitted towards the reflecting wall, and then once it hits the reflecting wall, it will change direction and move towards your receiver. So there are two components. Maybe I'll use different colors to show. There's one component that is coming directly. There is another component that's hitting the wall and getting reflected and then reaching the receiver. So you can write the signal arriving at the receiver as sum of two components, E direct plus E reflected. So the equation for E direct is alpha over some quantity times cos of 2 pi fc into 1 minus vc v over ct. This is due to the Doppler shift. So earlier in the previous question, we had seen that the Doppler was v cos beta by lambda. Here, the user is moving in this direction and the radiation is also moving in the same direction. So the angle that the direction of motion makes with the direction of wave propagation is 0 degrees. So cos beta is just 1. So the apparent frequency is fc into 1 minus v cos beta by lambda is just 1 minus v by lambda. So it's fc minus v cos beta by lambda. Lambda can be written as c over fc. So it's fc into 1 minus uh, v, v over c, v cos beta over c. Cos beta is 1, so it's 1 minus v over c. So that's the effect of the Doppler. And there's also there's another component which is the component due to the distance, initial distance from the transmitter to the receiver, which is so the other component is the phase change due to the time delay. So if you write phase is omega t is 2 pi f c t, then the change in phase due to the time delay. There's a time delay because the transmitter and receiver start out are initially R0 apart. So that time delay is um, we know that electromagnetic waves travel at the speed c. So it is the distance over time. So the time delay causes the distance over speed. Here for this red radiation, the distance r0 is what's causing the time delay. So it's r0 over c. So you have this component 2 pi fc into r0 over c, which is the change in phase due to the initial distance between the receiver and transmitter due to the time delay. So that component is 2 pi fc into, for the direct radiation, it's r0 over c. And here again, there's an attenuation because of the distance. So it's a linear factor of the distance between the transmitter and receiver. So at time t is equal to 0, you start out at distance r0, and the additional distance traveled in a time t is vt. So that's the total distance of the receiver from the transmitter at time t. So there will be an attenuation by that amount. So that's the direct component. Indirect component is pretty much the same. So now I will leave the indirect component to you. What is the attenuation to what is the distance and cos 2 pi fc. So direct or indirect, the Doppler is the same. 1 minus v over c times t minus here the phase shift due to. So this indirect component is traveling an additional 2d distance. So it has to go this way and come back. This is 2d distance on top of the r0 distance that it has traveled. So it's 2d plus, okay, you write it down yourself. What is the factor here? And one more thing you have to note is that when a radio wave hits a wall, its phase changes by 180 degrees. So that this is all from physics. Uh, so you have to go back and look at your physics textbook maybe. So when it hits the wall and it's reflected back, there's a 180-degree phase shift. And a 180-degree phase shift, so you know that cos of phi plus theta is minus cos theta. So you can write this as minus of alpha or whatever this way, or you can actually add that as plus or minus theta inside the phase term. Both are the same. So those are the direct and reflected components. And you add those up, you will get the equation of the received signal. Then question 16, the the difference between maximum and minimum Doppler shifts among all multipath components is called the Doppler spread. So this question asks what is the Doppler spread for this particular situation. And this is actually quite easy. You don't need to do any calculations. It's the difference between the maximum Doppler and minimum Doppler due to multipath. There are only two paths. So only two paths, direct and reflected. What is the Doppler caused by these two parts? The Doppler depends on the velocity v and the angle that direction of motion makes with the direction of radiation. And in this case, for both the direct and the reflected part, the angle that the direction of motion makes with it is zero. So both have same F, Doppler shift. That's why in your direct and reflected part, the effect of Doppler was the same. So Doppler spread is maximum minus minimum, but both are the same. What does that mean? I won't write it down, but it's pretty obvious. So when is there constructive interference? There is constructive interference when both the signals add up. Constructive when and it's constructive on interference only when they add up. That means they're in the same phase. Only then can you add two sinusoids directly. So you can say constructive interference when E direct and E reflected add up. So like I previously said, this minus you can take it inside and write it as plus pi or minus pi. In which case you'll have plus in both the terms. So then the constructive interference will happen only when the terms inside the uh, cosine function are equal. And when will that happen? You can see that in both the terms 1 minus v of ct are common, so that will be the same. Since it's a cosine function, it will repeat after every 2 pi angle. So in E reflected, you can write delta theta is the difference in phases 2 pi fc into 1 minus v over c t minus r0 over c minus 2 pi fc into 1 minus v over c t minus the other term from the reflected component, plus you can write a pi. So constructive interference occurs when the phase difference is 2m pi, that is an integral multiple of 2 pi. M is an integer. Even otherwise, also, if you don't know the formula, you can still solve this. If you, what we need is the phase difference between the direct signal and the transmitted signal to be an integral multiple of 2 pi. The phase difference is how much? So the phase difference is caused by the time delay. So alternatively, you can do it this way. If phi is 2 pi of ct, the phase is of course ignoring the Doppler effect. So the change in phase between the reflected and direct components is 2 pi f c delta t. And we know that c is delta s by delta t. So delta t is 2 pi f c delta s over c. So this is the path difference. This is the effect due to the path difference. That is the difference in distance that both the signals have to travel. There's also the reflection from the wall. So you have to add plus pi. This is due to reflections. Now, what is the path difference between the two um, signals? One signal is directly traveling from in that way. The other signal has to go a distance d, then travel back a distance d, and then start from this point. So the path difference is twice of d. So it's 2 pi f c over c into 2d plus pi. So delta phi is 2m 2 pi m. So 2 pi m is pi into 4 d over c plus 1. So 4 d over c is 2m minus 1. So here we didn't really know the uh, equation for the signal, but you can still solve uh, just using basic physics. Finally, question 18, we saw what the Doppler spread was. Question 18 asks, what is the delay spread? This delay spread is the maximum time delay divided by minus the minimum time delay, or you can say um, what's the time of arrival of the time signal that arrives the latest minus the time of arrival of the time signal that arrives the fastest. So here there are only two signals, direct component and the reflected component. If we take the time of arrival of the direct component as our reference, then Again, the time delay is only the extra time, additional time that the reflected component takes when compared to the direct component. We saw that it has to travel an additional distance of 2D. So we saw delta S was 2D, speed is c. So c is delta S over delta t. Delta t is delta S over c. So that's just your delay spread. This is just from physics. If you know the signal, then again you know we had two components in the signal. One was the Doppler, and the other is the and effect due to delay. So if you find the delay in the reflected signal, then the delay spread is the difference between these two delays. Alright, the other questions are theoretical questions which you can answer yourself. So that is it for today's session.